Hello, this is Neil Feit of the SUNY Fredonia Department of Philosophy. I'm doing a video here primarily for my logic students, fall 2019 Phil 116 students, but anyone can watch. I'm going to talk a little bit about doing proofs in the forall x system. And I'm looking here at some of the basic rules. I'm going to call your attention to a rule here. This is basically what we call modus ponens, but in this system we call it the conditional elimination rule. Okay? That third line down, B there, that's the conclusion of the rule. Okay, so this rule allows you to write down that conclusion if you have two premises. Okay, so these are labeled M and N. So the rule basically says this: if you have a conditional anywhere in your proof, a statement of the form if A then B, and if you have the antecedent A somewhere else on another line in the proof, you could write down B. Okay, and here with this rule, the arrow, the conditional operator has to be the main logical operator, and that's the case with all the basic rules, everything except rules of replacement. Okay, I'm going to say a few words about this, and then we'll do a couple of proofs. Here are some good examples of using this conditional elimination rule. All right. So, for example, here to the left, I have if J then K together with J, and I could write down K. Right? And I could justify that by saying conditional elimination from 1, 2. Okay? Here I have another pair of statements, not R, and if not R, then S. Okay? So the conditional doesn't have to be on top or above the antecedent. It could be below, and by the way, these lines could be separated by many lines in between them as well, so I would just get to write down S in this case, because the arrow there is the main operator, and it would be the same exact rule, conditional elimination, 1, 2, and maybe I won't write that for this third one. Notice here in this third one, this middle arrow is the main logical operator there, okay? So that says, the top line there says, if it's the case that if A then B, then it's true that if Q then U, and if on another line I have if A then B, then I could write down Q then U, and I could justify that by saying it's a conditional elimination from, I guess, 1 and 2. Okay, so those are some good examples. In this case, see here, we cannot use the conditional elimination rule. Okay, the reason being that the conditional there is not the main operator. The main logical operator of line 1 there is the disjunction symbol, the OR. So we could use these rules only when the pictured operators, right? When the pictured operators are main logical operators. And that's the case with all rules except rules of replacement. We could use a rule of replacement or a replacement rule. For example, if I wanted to use the rule of material conditional on if B then C, I could change that to not B or C. So what I would have to do is I would have to carry down the A or, and then inside the parentheses there I could use the MC rule. And by the way, I encourage you to have your rules out somewhere. You could take a look at them. I could use that MC rule, and I could change the if B then C to not B or C. Okay, so replacement rules of replacement work on parts of lines or subformulas, and so the operators pictured in those rules don't need to be main logical operators. So in this case, on my line 2, that follows from line 1 by the material conditional rule. Okay, let's do a couple of proofs. I have here an argument, and by the way, I encourage you to pause this video often and think out the proof in advance, do the work, and play the video when you feel the need to check your work or move on. So here we have 3 premises, and if this argument were giving to you on a single line, those premises would be separated by commas, and then the conclusion would be therefore D. D is the conclusion here of this argument. Okay. One tip in doing proofs is to work backwards a little bit. So for example, I see D, that statement there on line 2 of my proof. So here's a little bit of thinking. If I had not A by itself, I could use that with that rule that we were just looking at, conditional elimination, to get C or D. And then if I had not C, then I could get D by a disjunction elimination or disjunctive syllogism. So that's a little bit of, you could write some things out here in the margins here. You know, we would like to get not A in this proof, and we would like to get not C in this proof. If we had those on their own lines, we could get D. Okay. What we're going to do here is we're going to put in a little vertical line and a horizontal line under the last premise. That indicates that those premises are assumptions. Okay. So when I do proofs, I like to look for sort of three big rules: conditional elimination, modus tollens, and disjunction elimination. Okay, I can't yet do any of those, but I do see a conjunction here on line 3. So a good thing to think about is when you see a conjunction as your main logical operator, it's good to use the conjunction elimination rule on that. So I think I'm going to need both conjuncts. So I'll take them out. I'll take them out in order. I'm going to write not B on line 4, and I'll justify that by conjunction elimination from line 3. And I might as well just do not C. Also conjunction elimination from line 3. Okay. Now take a look at line 1 and line 4. Okay, premise 1 and line 4. Those have modus tollens form. Modus tollens is a derived rule, but it's a very common pattern of inference. And they let me conclude not A. So that was sort of on my little wish list that I wrote in blue a couple of seconds ago. So I can write down on line 6 not A. And the justification for that is modus tollens. And by the way, again, I strongly encourage you to have your sheet of rules or rules somewhere available to you. Line 6 is justified by modus tollens, and that comes from line 1, if A then B, and line 4, not B. Okay, that needs two premises, so you need to cite two lines when you use that rule. Okay, well now look at lines 2 and 6. They have modus ponens, or conditional elimination form. They let me conclude C or D. And I could keep those parentheses around the C or D if I wanted to, but they are optional when they're outermost parentheses. And again, that's conditional elimination, and this comes from line 2 and line 6. Okay, now lines 5 and 7 have disjunction elimination form, so I could get D. And I could write disjunction elimination. This pattern of it. So line 7 says that an OR statement is true, C or D. Line 5 says that C is false, not C, so D must be true. You could here write 7, 5, but if you want to write 5, 7, that's fine with me. And that's the proof. I'm going to do a few more today. So here's another tip. When the conclusion is a conditional, as in this argument, if B then not F, what we want to do is we want to use the conditional introduction rule. Okay, the conditional introduction rule, if you take a look at it, involves, in this case, assuming B, assuming the antecedent of what you want to prove, and then deriving not F in this case. Okay, so again, I'm going to start. We have three premises again here. I'm going to move my little line over here. Whoops. Okay, to get my main proof started, and I'm going to indicate that those three lines are premises. Okay, what I'm going to do here is I'm going to kind of indent a little bit, and I'm going to assume B basically, and I'm going to say that I want not F. That sort of gives me a goal here. Okay, and when you do this, okay, you need to that's sort of an assumption that B doesn't follow from the premises. You can't conclude B from the premises. So we're going to indicate that with another little subproof going on here. Okay, I'm assuming B for the purpose of showing that F, or not F rather, follows from it. For the purpose of showing if B then not F. Okay, making this assumption now hooks up with line 1, conditional elimination. I could get G. Okay, so that's conditional elimination from 1 and 4. Okay. Now, something a little bit new here maybe. You might be stuck at this point thinking, oh, what do I do next? Okay, obviously we want to get not F. That's our goal here. We want not F on its own line. Okay. I don't see anything that I can immediately use here, okay? I could do an assumption of F for reductio if I'm stuck, but look at that line 3, premise 3 here. It's not the case that both G and N are true. I'm going to use the De Morgan's rule on that, okay? I'm gonna transform that into something that is logically equivalent to. If you look at the De Morgan's rule, it's a pretty common rule, useful to get the hang of and know. If not both G and N are true, then it follows that not G or not N are true. Okay. So what I just wrote down on line 6, that follows by the De Morgan's rule from line 3. Premise 3. Okay. Now at this point, lines 5 and 6 are pretty close to having disjunction elimination or disjunctive syllogism form. And in fact, I guess if you did this on one of my tests or exams or problem sets, I probably would let you do that. Use line 5 and 6 for disjunctive syllogism. But if you really look at that disjunction elimination rule, you need an or statement. By the way, I could get not F if I had not N, right? Modus tollens. So I kind of want to get not N. Okay, so if I could get not G, if I could get the negation of not G, I could get not N from line 6. So what I'm going to do, I'm going to make this official. I'm not just going to conclude not N from 5 and 6. I'm going to look at line 5, and I'm going to do a double negation. I'm going to get not G. I'm going to do a double negation from line 5. And now, officially, line 6 is an or statement. Okay, either not G or not N. And line 7 is the negation of not G, not G. Okay, so I could get not N. Okay, so that is the disjunction elimination rule from 6 and 7. Okay, so now at this point we have, and by the way, I have a short arrow. Let this inner rightmost vertical line go down a little bit. Now not N hooks up with line 2 to give me not F. So not F follows from modus tollens from lines 2 and line 8. Okay, so I could maybe bring this down a little bit. There we go. And maybe I could bring this down a little bit. Okay. Oop. Okay. Don't know quite what is the problem here, but my line 10 should be closer to the number 10. But if you look at the logic in lines 4 through 9, we have assumed that B is true and shown that not F is a consequence, so we have therefore proved if B, then not F. And that is the arrow introduction rule, which was our tip here. And in this case, we cite all the line numbers in the subproof, 4 through 9. And ideally, that B then not F should be closer to the number 10, so kind of right under. I don't know quite why. There it goes, that way, on line 10. So that's how the proof should look there. We're going to do another proof for true. We're going to try to keep this in the neighborhood of a 20-minute video. We'll do our best. We'll see. If you're ever stuck, don't forget indirect proof. Indirect proof is assuming the opposite of what you want to prove, so we call that an assumption for reductio, and that's our negation rules, negation introduction or negation elimination rules. I recommend these rules, especially if you're stuck not knowing what to do next in a proof. So again, here we have an argument. You can take a look as I set things up. I have two premises here, and the conclusion that follows is not A. Okay. If you look at these two premises, they're both conditionals. And we can't use conditional elimination here. No modus ponens. We can't use modus tollens. We can't use a disjunction elimination. There's no conjunctions to simplify or conjunction elimination. Okay. And we want to prove not A. Okay. So the best way to do this is just to assume A. Okay, assume the opposite of what. And if we could show that A leads to a contradiction, then we've shown that A can't be true, and as a result that not A is true. Okay, so I'm going to make that assumption. And what I'm going to do here is I'm going to start a subproof, as we did in the proof above. This is the only other situation, besides conditional introduction, the only other situation, in statement logic anyway, where we're going to need a subproof. Okay, which is sort of this second vertical line going with an indentation. Okay. Now, having assumed A here, I want to note that it's for reductio, and that is my not reduction, my reminder that I want to now try to prove a contradiction. It could be A and not A, B and not B, D and not D. Okay. Okay. Well, look at premise 1 here. It says if A or B is true, then C and D are true. Okay. Well, look at my assumption, line 3, A. What I can do is I could conclude that A or B is true on the basis of line 3 alone. If A is true, then A or anything is true. Okay? We have a rule for that. We call that disjunction introduction. And line 4 follows from line 3. If A is true, then A or B is true. In fact, A or anything is true. Why did I add or B to my line 3A? Well, now line 4 is the if part, the antecedent of line 1. So 1 and 4 have arrow elimination form, and I can conclude C and D. Okay, so arrow elimination, 1, comma, 4. Does that look right? Okay. I'm just going to think about this. If I made an assumption for reductio here, I'm going to need, officially, to use that rule, I should have like a statement and its negation on consecutive lines here. Okay? And what I'm thinking here is I could get D from here, and with my C, I could get not D here. So I'm kind of thinking that my contradiction here is going to be D and not D. And so what I'm going to do is I'm going to plan ahead. I'm going to simplify or use my conjunction elimination. I'm going to get C on line 6. So that's going to be my conjunction elimination from line 5. And I'm going to get my D also from conjunction elimination line 5. Okay. Now with C on line 6 and premise 2, which we haven't used yet, I could get not D. And that is modus ponens, right? Or as we call it here in our proof system, conditional elimination. And that uses 2 premises, in this case 2 and 6, right? 2 comma 6. Okay. Check out the logic here. Assuming A was true, given the premises, assuming A was true on line 3, that leads to a contradiction, both D and not B, D being true. That's impossible. So hence A cannot be true. As a result, its negation, not A, is true. And that's the end of this proof. And the logic here is, in this case, we're introducing a negation, so it's negation introduction, and we cite 3 through 8, 3 through 8, all the lines in the subproof. Okay, I'm going to do maybe just one more and then give you a super quick introduction to quantified logic. Little refresher for some of you, and maybe something new for some of you as well. Okay, this last proof is going to emphasize another tip. To show a disjunction, any statement of A or B form, it is often useful to show if A then B. And we have this rule, material conditional. It's a rule of replacement. It lets us transform if A then B into A or B, and vice versa. Okay. So another good strategy, by the way, is to assume the opposite of what you want to prove. You could always assume not A or B for reductio, and not A or B is a statement that you could use the De Morgan's rule on, so you could use and then break that up. I'm going to use, though, the strategy of wanting L or M in this case. So I'm going to assume in this case not L and try to prove M. Okay, we'll do it that way. So as I set this proof up, you could think about it a little bit. Maybe I will copy this if I can, paste it down here maybe. Copy this perhaps up here, paste it down here. Okay. Oops. Okay. So I have if J or K, then L, and I have if not J, then M. Again, we can't do anything like modus ponens or modus tollens or disjunction elimination. There's no conjunctions to eliminate. So let's assume not L and try to show M. Okay? We'll try to show that if L is false, then M is true, to prove that either L or M is true. Okay? So we basically want to show now a conditional. We want to introduce a conditional. So we're going to use that conditional introduction rule. We're going to assume not L, okay, and we're going to want M. And when we do this, we are starting a subproof. Okay. That assumption is useful because now lines 1 and 3 have modus tollens form. Okay, if you need practice, pause for a moment and think about what the conclusion is by modus tollens of from lines 1 and line 3. Okay, it's going to be the negation of J or K. So not, and you need the parentheses there, J or K. And that's going to be modus tollens from 1, 3. Okay. Now I have line 4, something that I can demorganize. I could apply De Morgan's rule to it. A negated disjunction, you should definitely be thinking of De Morgan's rule with that. So it's going to be equivalent to not J and not K. Okay, so that line 5 follows by De Morgan's from line 4. And look at line 2. If not J, then M. That's going to help me out a lot. I could take line 5 and I could eliminate that conjunction. I could get not J. Conjunction elimination from line 5. I don't even need not K, I don't think, in this proof. Okay, and now I could get M. That is from lines 2 and 6 by modus ponens, or as we call it here, conditional elimination from 2, 6. Now I have assumed not L and have shown that M follows, so I have proved if not L, then M. Okay, that's arrow introduction to 3 through 7. I'm kind of rushing here, but you could pause this at any time. I just want to keep this video certainly under 25 minutes, hopefully. Okay, so I think that works. And not L, then M is equivalent to our conclusion, L or M. And what I've just done now is I've used the material conditional rule on line 8. That was sort of the strategy of this proof. Okay. By the way here, what I could have done here is I could have assumed negation, I could have assumed not L or M. I could have assumed that for reductio, and then by De Morgan's I get not L and not M. And then with not L I could have done something similar to what I got here. And then with not M, again, when you make an assumption for reductio, we could have had the M and not M contradiction there. So the proof is pretty straightforward, doing it by reductio, assuming the opposite, negation parenthesis L or M, if you wanted to do it that way. Okay, what I'm going to do here is just give you a super quick introduction to adding quantified logic to our system of proofs. So I'm going to we're going to have an introduction and an elimination rule for each quantifier symbol. So universal introduction, universal elimination, existential introduction, and existential elimination. And I'm not going to talk about all those rules right now. And we're going to have quantifier negation rules of replacement. Not all is equivalent to some not. There does not exist is equivalent to everything is not. There does not exist an A thing. Everything is not an A thing. Okay, I'm just going to talk about universal elimination and existential introduction today, just to give you a little bit of an introduction here. Suppose everything is an apple for all x ax. Then we can conclude that any specific thing is an apple. Charlie's an apple. Okay, so here's the picture of our existential elimination rule. It's a pretty straightforward rule. Okay, here AC is what we call a substitution instance of AX. Okay, so the conclusion of this rule is just like AX, except every occurrence of X is replaced with a constant C. And we use C here in the picture of the rule because it's a constant. An individual constant is like a name, a lowercase letter in quantified logic. Okay, so we're replacing every occurrence of X in AX with C, and it doesn't have to be C here. If you need the letter D or something, or N in a proof, it could be N. So it's just a picture of the rule that has a lowercase c for constant. Okay. The only other rule that I'm going to do right now is existential introduction. Suppose that Charlie's an attorney. Obviously, it follows that something is an attorney. Okay. That's called, we're introducing an existential here. Here's the picture of that rule. It has one conclusion, the existential statement. The bottom line is the conclusion. The top line is the premise. So if AC is true, then there exists an X, AX is true. And just as in the previous rule, the premise here must be a substitution instance of AX. Okay, must be every occurrence of C must be replaced by X. Excuse me, every X is replaced by C in the premise. So there's your existential introduction rule. We have two other rules for the quantifiers which are a little bit harder to rationalize in a proof system, so we're going to need to put some restrictions on them in order to make them able to prove valid arguments, but only valid arguments. Okay, these two rules don't need any. So if you look at this here, line 1 here might be like all snakes are poisonous, all S things are P things, and the conclusion is if Charlie's a snake, then Charlie's poisonous, and that's a good legitimate use of universal elimination, the universal elimination rule here. Okay, so in the picture of the rule, the formula after for all x, the woof there might look simple, but it doesn't have to be. Okay, here Sx arrow Px equals our Ax. Okay, so real quick now, we're gonna prove this valid argument. Everything is beautiful. Every beautiful thing is good. Therefore, something is good. By the way, the conclusion that everything is good also follows here, and we're gonna do that in class if you're one of my students. If you want to pause and symbolize, that's fine. The proof here is going to look like this. Here's everything is beautiful for all x bx. Here's every beautiful thing is good for all x if bx then gx. And there's our conclusion. Something is good. Okay? We want there exists an x, that x is good. Okay? It doesn't really matter what order, but we're going to use a universal elimination here. We can't use conditional elimination on line 1 and 2 because with line 2, the universal quantifier is the main logical operator, not the conditional. Okay, so I'm going to use universal elimination on line 1, and I'm going to say Charlie's beautiful. And I'm going to use universal elimination on line 2. If Charlie's beautiful, then Charlie's good. Now I could use conditional elimination on 4 and 3, or 3 and 4, to get Charlie's good. And if Charlie's good, then something is good. Okay? So there's a proof, the first proof that we're doing as a class, and I hope this video has been useful. Signing off for now.